Hi, today we are looking at the work energy theorem for net force, so this should be more review. So for work energy theorem, for work done on an object will be equal to its change in kinetic energy. So from this we get two equations. So we have our basic work is equal to our change in kinetic energy, but of course we can substitute in formulas for both our work and our change in kinetic energy, which gives us our force parallel times our distance is equal to 1/2 our mass times our final velocity squared minus our initial velocity squared. So we'll utilize this in a couple examples. So first example, we have a pinball machine in which we're compressing a spring 15 centimeters utilizing a force of 110 newtons. When released, that spring pushes the ball that is 0.1 kilograms, and we already know what that ball is accelerated to in terms of velocity. So writing out what we have our force parallel, we have our mass, we have our distance, which was in centimeters, so we need that in meters, and we know our initial velocity is 0 because we assume it starts stationary, and we're solving for our final velocity. So we have our equation, our force times distance is equal to 1/2 times mass times final velocity squared minus initial velocity squared. Because our initial velocity was 0, we can get rid of the initial velocity squared to simplify our equation a bit. So we've got our force times distance equals 1/2 our mass times final velocity squared. I would next get rid of a 1/2 by multiplying both sides by 2. And then move the mass to the other side by dividing both sides by it. Lastly, we want to get rid of the squared, so we'll take the square root of both sides. At this point, we have a variable that we're solving for on its own, so we would substitute our values in. At this point, we'll calculate that and round to appropriate amount of significant figures, so that gives us 18 meters per second. Okay, next example, we have a 2 kilogram ball is rolling on a surface with a velocity of 12 meters per second. If after 15 meters it has slowed down to 8 meters per second, we want to know what the force of friction acting on it is. So things that we know off the start is our mass is 2 kilograms, our initial velocity is 12 meters per second, our final velocity is 8 meters per second, and it traveled a distance of 15 meters. We're solving for a force of friction, which in this case would be our force parallel. So we'll use the same equation as last time. So we've got our force parallel times our distance is equal to 1/2 times our mass times our final velocity squared minus our initial velocity squared. Now in this case, we just need to get force on its own, so I would divide both sides by our distance. At this point, because we have that force on its own, we can substitute our values in. And once again, calculate and round to appropriate amount of significant figures, which gives us a force of friction of negative 5.3 newtons. Okay, so we'll look at one more example before going into some more notes. So a 15 Newton ball is thrown upwards with a constant force of 65 newtons. If the force is applied for 40 centimeters before the ball is released, with what velocity is the ball released at? So we have a force applied of 65 newtons. Force of gravity is acting downwards at 15 newtons. We have a distance that we're in contact with the ball for, which is 40 centimeters, which is 0.4 meters. We're assuming we are starting stationary, so our initial velocity is 0, and we're solving for final velocity. So once again, we'll utilize the same formula. Our force times distance is equal to 1/2 times our mass times our velocity squared minus our initial velocity squared. Now, we need to figure out what our mass is, so I'll use our force of gravity equals mg. Rearranging that to get mass on its own, we divide both sides by g, substitute our values in, and we have a mass of 1.53 kilograms. And then for our force parallel, we also need to get our net force. So we'll look at sum of our forces, which is our force applied plus force of gravity. So 65 plus negative 15. So we have a net force of 50 newtons of being applied to this ball. Now that we've done that, we'll do some rearranging of our equation. So I'll do a couple things in this first step. So one is we can get rid of our initial velocity because it is 0. If others, I'll multiply both sides by 2 to get rid of a 1/2. At this point, divide both sides by our mass to move it to the other side. And then we'll take the square root of both sides to get our velocity on its own. And we can substitute our values in. And we get a velocity of 5.1 meters per second. Okay, so next we're going to talk a little about vertical situations. So for situations in which an object is lifted vertically at a constant velocity, we can use a potential energy due to gravity formula to equal our work. So our change in gravitational potential energy would be equal to our work. Now, if you recall from Physics 11, our potential energy of gravity is just mg times change in y. So, an example, a motor lifts an elevator with people in it 25 meters at a constant velocity. If the elevator and people's combined mass is 1,500 kilograms, how much work must the motor do? So we know our change in y, of our mass, we have gravity, which if you recall for energy, we don't bother putting in a negative with. And our work is equal to our change in potential energy. So we'll use our potential energy is m times g times change in y. We have all that information. We don't have to rearrange. So we have our work is 3.7 times 10 to the 5 joules. Power is our rate of doing work. If you recall, it is measured in watts, and it is equal to work divided by time, or our change in energy divided by time. So we can say power is work over time. We can also say it's our change in energy over time. Okay, so for example, we have a 40 kilogram box is pushed across a horizontal surface. It is accelerated to 20 meters per second from rest in 5 seconds. What is the power required to push this box? So first, write out the information we know. We know if the mass of the box is 40 kilograms. We know it's starting at rest, so our initial velocity is 0. We know our final velocity is 20 meters per second. We're given a time of 5 seconds. So we know power is either work over time or change in energy in time. So I've chosen to use our change in energy divided by time. We could do work over time as well. So if we have change in energy over time, that would be our change in kinetic energy divided by our time. Now our change in kinetic energy we know is 1/2 times our mass times v squared minus v naught squared. We can substitute our values in at this point, and we get 1.6 times 10 to the 3 watts. Now we could have done it with work instead. If we had done it with work instead, we would have had to use kinematic formulas to solve for acceleration, and then use that acceleration to get, and the mass to get a force, and then we could have used the force and the distance to get our amount of work. Either way gets us the exact same answer. Now, if there was a friction force involved, I would have had to utilize the other method. Okay, next we're looking at reviewing efficiency. So if you recall, we had 4 efficiency equations. The first 2 just give us efficiency as a decimal. Well, the second 2, we just multiply that decimal by 100 and add a percentage sign to get our efficiency as a percentage. And essentially it's amount of work out divided by the work in, or the power output divided by the power input. So we'll look at an example. A 1,500 kilogram elevator is pulled upwards at a constant velocity of 2 meters per second by a 50 kilowatt motor. Want to calculate the percent efficiency of the motor. So our mass is 1,500 kilograms. We have a power input of 50,000 watts. We know gravity is 9.81 meters per second squared, and our velocity is a constant 2 meters per second. So if we look at our power equation, we know power is work over time. Now in this case, our work is actually going to be our change in potential energy. Now we know our change in potential energy can be written as mg change in y. But what we're going to take particular attention to is our change in y and t, because our change in y is a displacement and our time is measured in seconds. So if we have a displacement and divide by a time, that is a velocity, so we can simplify and change this equation into mgv. At this point, substitute our values in, and we get a power output of 29,430 watts. Now our percent efficiency is power output divided by power input. We'll multiply by 100 and add a percentage point or symbol. So our output we just calculate, our input we're given. Calculating that gives us an efficiency of 59%. Okay, so next we're going to look at mechanical energy. This is the kinetic energy of an object and the potential energy of an object. Now these two energies are considered to be mechanical energies. So if only conservative forces act on an object, the mechanical energy of the object does not change. And this is essentially what the law of conservation of mechanical energy is. Now, a conservative force is a force that, if when moving from one point to another, the amount of work required does not depend on the path taken. Now, gravitational forces are considered to be conservative because if we lift something straight up or lift it at a diagonal, the amount of gravitational force we're fighting against is a constant. Now, frictional forces are not conservative, so anything that has a friction force would not be considered for our law of conservation of mechanical energy. So we can only have conservation of mechanical energy in a frictionless system. For conservation of mechanical energy, when our mechanical energy is conserved, any increase in one type of energy will cause an equal decrease in another type of energy. So if we lose, say, 100 joules of kinetic energy, we gain 100 joules of potential energy, or vice versa. Now from this, we get our change in kinetic energy plus our change in potential energy equals 0. So if one increases, the other has to decrease by the same amount to maintain that equals to 0. Okay, with this example, we have a 0.25 kilogram ball is thrown upwards with an initial velocity of 15 meters per second. If the mechanical energy is conserved, we want to know how high the ball goes before coming back down. So we know our mass is 0.25 kilograms, our initial velocity is 15 meters per second, our final velocity is 0 meters per second, and we're solving for our height. Now we know our final velocity is 0 meters per second because in Physics 11 we learned that at the very top of a flow before coming back down, we briefly have a velocity of 0. Now we're going to use our change in kinetic energy plus change in potential energy equals 0. We'll move the change in potential energy to the other side of our equation. And then substitute formulas in. So we have 1/2 our mass times our final velocity squared minus initial velocity squared equals negative of mass times gravity times our change in y. Now, both sides have mass in them, so we'll cancel that out. Also, we know our final velocity is 0, so we can get rid of that term. So that gives us 1/2 times negative of our velocity squared, or initial velocity squared, equals negative gravity times y. Now you'll notice we have a negative on both sides, so we can cancel that out. Now we're trying to solve for y, so at this point I divide both sides by our gravity, and we can substitute our values in, and we end up with 11 meters. Okay, next example, a 0.5 kilogram ball is thrown downwards at 15 meters per second from the top of a 100-meter tall building. With what speed does it strike the ground? So our mass is 0.5 kilograms. Our initial velocity is 15 meters per second. We know our y is going to be negative 100 meters. Our v we are looking for, and we've got our change in kinetic energy plus change in potential energy due to gravity equals 0. I'll move our change in potential energy to the other side of our equation and substitute in equations for each side. Now, once again, we've got mass on both sides, so I can cancel out. And then we need to rearrange to get final velocity on its own. So first thing I would do is multiply both sides by 2, so that will get rid of a 1/2, enabling us to drop the brackets on the left side of our equation. I'd then add the v0 squared to both sides, and then take the square root of both sides. At this point, we can substitute our values in, and we get 47 meters per second. Okay, so our last example, we have a 25 kilogram box is placed on a frictionless incline. It is inclined at 30 degrees above the horizontal. If the box starts 15 meters up the slope of incline, what will its speed be at the base of incline? So we know our mass is 0.25 kilograms. Our initial velocity is 0 meters per second. Our final velocity we're looking for. We also know we're going to need to find our change in y, so we need to solve for that as well. So as part of this question, I'll also draw out our situation. So we have an incline that's inclined at 30 degrees, and the slant of it is 15 meters long. Now we'll use our conservation of mechanical energy formula. So change in kinetic energy plus change in potential energy equals 0. We'll move our change in potential energy to the other side of our equation, substitute in our equations for that. Our mass is going to cancel on both sides. I would multiply both sides by 2 to get rid of the 1/2 and drop the brackets. Now we also know that our initial velocity is 0, so we can get rid of our v0 squared and then take the square root of both sides. Now we don't know our y yet, so we can't fully substitute our values in. So if we look at our triangle, our y would be our opposite side. We have our hypotenuse, so I would use sine. Sine we know is opposite over hypotenuse. If we multiply both sides by a hypotenuse, that gives us hypotenuse times sine is equal to our opposite, or hypotenuse times sine is our y value. So I'll just substitute that directly into our equation. So v is equal to the square root of negative 2g times our hypotenuse sine of our angle. And substituting values in, that gives us 12 meters per second.